Hello to all my viewers. I am Praveen Karthik and today we are going to talk about imaging missions, particularly the Nancy Grace Roman Space Telescope by NASA. It was named after the famous American astronomer Nancy Roman. Imaging missions capture images about planets, exoplanets, stars, nebulae, supernovas, etc. They use a spectral analysis of the time series data and plot values on a graph, which contains numerous important information. Before going further into this topic, I hope you have listened to my introductory topics. They'll help you appreciate this topic better. Let's begin. Many time series show periodic behavior. This periodic behavior can be very complex. Spectral analysis is a technique that allows us to discover underlying periodicities. To perform spectral analysis, we must first transform data from the time domain to the frequency domain. Spectroscopy is used for all spectrums and encompasses various approaches depending on the type of outcome needed. It involves measuring accurate wavelengths of emission and absorption lines, relative strength or equivalent widths of emission or absorption lines, shapes of emission or absorption lines, or spectral energy distribution of the continuum radiation. For more reading, you can refer Spectroscopy for Amateur Astronomers by Mark Tripstein and Richard Walker. Single slit spectrographs are often used in a variety of scientific and technical applications, including the analysis of the chemical composition of samples, the study of the properties of materials, and the measurement of the velocity of object. One advantage of a single split spectrograph is that they are relatively simple and inexpensive to build and operate, making them a useful tool for a wide range of applications. However, they are not as precise as more complex spectrographs that use multiple slits, and they are not as efficient at separating the different wavelengths of light. A grism, also known as a grating prism, is a combination of a prism and grating arranged so that the light at chosen central wavelength passes straight through. A diffraction grating is an optical element that divides or disperses light composed of lots of different wavelengths, example white light, into light components by wavelength. The simplest type of grating is one with a large number of evenly spaced parallel slits. Wide field can mean many things. V. Lipovetsky defined it as imaging with 10 raised to 7 to 10 raised to 3 elements or pixels per field. There are other possibilities. For neutrinos, gravitational radiation, cosmic rays, and some kind of gamma rays, the whole sky is a single, very wide field. Arcs are extremely small units of measurement. An arc minute is 1 upon 21,600th of circumference. An arc second is 1 upon 1,296,000 of 360 degrees. Dark energy is a mysterious form of energy that is thought to exist in order to explain the observation that the expansion of universe is accelerating. This acceleration was first discovered in the late 1990s and it has been confirmed by multiple independent studies since then. The new NASA's James Webb Space Telescope has also confirmed that the universe is not just growing at a really fast rate, but that we might also have parallel universes. The existence of dark energy is inferred from its gravitational effects on the expansion of the universe, but its nature and properties are not well understood. It is thought to make up about 68% of the total energy density of the universe, but its composition and behavior are not known. Dark energy has been thought to form from the Big Bang, through which normal energy and dark energy was formed. The same way matter and dark matter was formed. There are a number of theories about the nature of dark energy, but none of them have been conclusively proven. Some scientists believe that it may be a property of space itself, whilst others think it could be due to the presence of a new field or particle that has not yet been detected. An exoplanet is any planet discovered which is not present in the solar system and can be gas giants like HAT P69b or super Earths like MOA 2007 BLG 192LB, which need further investigation to reclassify them into categories, but cannot be done entirely because they are hundreds and even thousands of light years away. Photometry is the science of measuring the intensity of light. It is used to study the properties of light sources such as stars and galaxies and to measure the amount of light that is received from these sources. One method of photometry is direct imaging photometry, which involves taking an image of the light source with a telescope or other imaging device and measuring the brightness of the source in the image. This can be done by comparing the brightness of the source to that of nearby reference stars or by using a calibrated detector to measure the total amount of light received from the source. Direct imaging photometry is a useful tool for studying the properties of light sources, such as their luminosity, temperature, and size. It can also be used to measure the distance to a light source by comparing its apparent brightness to its known intrinsic brightness. CCD stands for Charged Coupled Device. It is a type of image sensor that is commonly used in digital cameras and other imaging devices. A CCD sensor works by converting light into an electrical charge. Each pixel on the sensor is capable of detecting and measuring the amount of light that falls on it. The charges generated by the pixels are then processed to create a digital image. An EMCCD, electronic multiplying CCD, is a special type of CCD sensor that is designed to be more sensitive to light compared to a regular CCD. This increased sensitivity is achieved by using a special amplification circuit that multiplies the charges generated by pixels. EMCCD cameras are often used in applications where low light levels or high sensitivity is required, such as deep space astronomy. In this type of application, the EMCCD camera is used to capture images of faint objects in the universe, such as distant galaxies and nebulae. The increased sensitivity of the EMCCD camera allows it to detect and measure the light from these faint objects, which would be difficult or impossible to detect with a regular CCD camera. A Lagrange point, named in the honor of Italian French mathematician Joseph Louis Lagrange, is a point in space where the gravitational forces of two large bodies, such as Earth and the Moon, balance at the centrifugal force felt by a smaller object, such as a satellite, at their location. In other words, at Lagrange points, the gravitational pull of two large masses precisely equals the centripetal force required for a small object to move with them. This allows the smaller objects to remain in a stable position relative to the larger bodies. At these points, objects in there tend to stay put. These points in space can be used by spacecraft to reduce fuel consumption needed to remain in position. This can be especially useful for missions that require a spacecraft to remain in a specific location for an extended period of time. There are five Lagrange points designated as L1 through L5, and they are labeled according to the locations where they exist relative to the two larger bodies. The unstable Lagrange points, labeled L1, L2, and L3, lie along the line connecting the two large masses. The stable Lagrange points, labeled L4 and L5, form the apex of two equilateral triangles that have the large masses at their vertices. L4 leads the orbit of Earth and L5 follows. Lagrange points have been used in a number of space missions, including the placement of the Solar and Heliospheric Observatory (SOHO) at the L1 point to study the Sun, and the placement of the Chandra X-ray Observatory at the L2 point to study distant objects in the universe. The Nancy Roman mission will be deployed to L2 Lagrange point and is expected to have an approximate lifetime of 5 years after launch. Why is this mission important? This mission's wide field of view will allow it to generate never before seen big pictures of the universe, which will help astronomers explore some of the greatest mysteries of the cosmos, including the expansion of the universe seems to be accelerating. One possible explanation for this speed up is dark energy, an unexplained pressure that currently makes up 68% of the total content of the cosmos and may have been changing over the history of the universe. Another possibility is that this apparent cosmic acceleration points to the breakdown of Einstein's general theory of relativity across large swaths of the universe. The Nancy Grace Roman Space Telescope will have the power to test both of these ideas. To learn more about dark energy, the Nancy Grace Roman Space Telescope will use its powerful 2.4 meter mirror and wide field instrument to do two main things: map how matter is structured and distributed throughout the cosmos, and measure how the universe has expanded over time. In the process, the mission will study galaxies across cosmic time, the present age back to when the universe was only half a billion years old, or about 4% of its current age. The Nancy Grace Roman Telescope will do this through multiple observational strategies, including surveys of exploding stars called supernovas and galaxy clusters, and mapping out the distribution of galaxies in three dimensions. Measuring the brightness and the distance of supernovae provided the first evidence for the presence of dark energy. The Nancy Grace Roman Space Telescope will extend these studies to greater distances to measure how dark energy's influence has increased over time. The Nancy Grace Roman Space Telescope will measure precise distance to galaxy clusters to map how they grew over time. The mission will also pinpoint the distances to millions of galaxies by measuring how their light becomes redder at greater distance, a phenomenon called as a redshift. The farther off the galaxy is, the redder its light appears when we see it. Mapping out the 3D position of galaxies will allow astronomers to measure the distribution of galaxies and how it has changed over time, providing another measure of how dark energy has affected the cosmos. The wide field instrument will also allow the Nancy Grace Roman Space Telescope to measure the matter in hundreds of millions of distant galaxies through a phenomenon dictated by Einstein's relativity theory. Massive objects like galaxies curve space-time in a way that bends light passing near them, creating a distorted, magnified view of far-off galaxies behind them. Using this magnifying glass effect called weak gravitational lensing, the Nancy Grace Roman Space Telescope will paint a broad picture of how matter is structured throughout the universe, allowing scientists to put the governing physics of its assembly to the ultimate test. The Nancy Grace Roman Space Telescope can use the same light bending phenomenon to study planets beyond our solar system, known as exoplanets. In a process called microlensing, a foreground star in our galaxy acts as the lens. When its motion randomly aligns with a distant background star, the lens magnifies, brightens, and distorts the background star. As the lensing star drifts along in its orbit around the galaxy and the alignment shifts, so does the apparent brightness of the star. The precise pattern of these changes can reveal planets orbiting the lensing star because the planets themselves serve as miniature gravitational lenses. Such alignments must be precise and last only hours. The Nancy Grace Roman Space Telescope's microlensing survey will monitor 100 million stars for hundreds of days and is expected to find about 2,500 planets, with significant numbers of rocky planets in and beyond the region where liquid water may exist. This planet detection method is sensitive enough to find planets smaller than Mars and will reveal planets orbiting their host stars at distances ranging from closer to Venus to beyond Pluto. These results will make the Nancy Grace Roman Space Telescope an ideal companion to Mars's missions of NASA, like the Kepler and the upcoming transiting exoplanet survey satellite, which is the TESS, of course, which are best suited to find larger planets orbiting closer to their host stars. And together, discoveries from these three missions will help complete the census of planets beyond our solar system, helping us learn how planets form and migrate into systems like our own. Under current plans, the Nancy Grace Roman Space Telescope will have a primary mission lifetime of 5 years and is being designed to support 5-year extended mission. A fuel is the only expendable. We will now understand how the mission is constructed. It contains many modules, and each module is currently at different stage, starting from design all the way until testing. These modules are the wide field instrument, the telescope itself, communication system, the solar array sun shield, observatory support systems, and coronagraph. The ground support system has many components such as antennas, mission operations center, science operations center, science support center, coronagraph technology center, flight dynamics operation area, just to name a few. As the primary instrument, the wide field instrument will measure light from a billion galaxies over the course of the mission's lifetime. In addition, it will perform a microlensing survey of the inner Milky Way to find approximately 2,600 exoplanets. The Nancy Grace Roman Space Telescope's coronagraph instrument, Roman coronagraph, will perform high contrast imaging and spectroscopy of dozens of individual nearby exoplanets. Lights from an exoplanet, as it would be seen in reflected starlight, is fainter than the host star by factors of 100 million or more, and well beyond the reach of today's observatories on ground or even in space. The Nancy Grace Roman Space Telescope coronagraph instrument will demonstrate the first high performance coronagraph system in space capable of imaging directly mature gas giant exoplanet systems similar to our own Jupiter and Saturn in reflected starlight, paving the way to a future possible NASA mission aimed at imaging and characterizing faint Earth like planets. A wide field module is a 300 megapixel infrared camera that allows scientists to explore the cosmos all the way from the edge of our solar system to the farthest reach of space, and has some interesting equipment. It has the mosaic plate assembly, the MPA, which holds the detector array mosaic, the heart of the wide field instrument WFI. It consists of 18 highly sensitive large format detectors arranged into an arch-shaped mosaic. Each detector contains more than 16 million pixels that collect visible and infrared light emitted by astronomical sources. These devices will convert the light and they collect into electrical signals, which will then be decoded into enormous images. Combined, the 18 detectors in the array comprise a wide field imaging camera with more than 300 million pixels. The detectors operate cold at negative 178 degrees Celsius to reduce electronic noise and thermal backgrounds. The detector array mosaic will enable the WFI to perform deep surveys of large portions of the sky to study dark energy, exoplanets, and more. Next is the focal plane electronics FPE. Box is the command center of the wide field instrument detectors. It contains electronic components that command each detector in the mosaic, relaying instructions that can be fine tuned for different science observations. The electronics will also provide power to the detectors and perform onboard data processing and compression. The elemental wheel assembly EWA is a large disc mode of lightweight metal placed in front of the detector array. It has slots around its perimeter that contain a calibration hardware filters for imaging and the grism and prism for spectroscopy. The element wheel allows the spread of light of astronomical objects into spectra. The wheel rotates at its central axis to bring different elements into the light path, changing the instrument's observations. The element wheel is in a housing that contains heaters to hold the wheel and various elements at a constant temperature and limit distortion in the optics. The element wheel contains the filters, grism, and prism. The filters are made of glass with special coatings that only allow light in carefully chosen wavelength bands to reach the detector array. The grism and prism each contain several custom optics designed to spread the light from cosmic objects into spectra over a wide wavelength range. The WFI will combine imaging using the filters and spectroscopy using the grism and prism to study galaxies and supernovae to help us understand dark energy. Observing stars using the filters will reveal exoplanets via a technique called gravitational microlensing. This observational effect occurs because the presence of mass wraps the fabric of space-time, When two stars closely align from our vantage point, the nearest star and any orbiting planets can lens light from the farther star, making it briefly brighten. The WFI thermal system keeps the instrument subsystems at their ideal operating temperature. A system of metal straps and heat conducting pipes will carry heat produced by the detectors and electronics to radiator panels that face cold space on the outside of the instrument. The excess heat will be radiated away, cooling the instrument components. Thermostats and heaters will be precisely monitored and control the subsystem temperatures, holding them in a narrow and stable range so that the observations won't be impacted by swings in temperature that introduce uncertainty in the precision scientific measurements. The telescope has quite a few more instruments, such as the primary mirror assembly (PMA), includes the telescope's main mirror and its supporting structure. Mirror has a diameter of 2.4 meters and will be cooled to about minus 7 degrees Celsius. The secondary mirror assembly, the SMA, includes the telescope's secondary mirror and its supporting structure. The mirror has a diameter of 5.81 centimeters and will again be cooled to about minus 7 degrees Celsius. The SMA is positioned by 6 alignment drives and 2 focus drives to align with the primary mirror. The aft optics module, the AOM, consists of 3 optics and the supporting structure to relay the light beam to the WFI. It has a concave tertiary mirror and 2 flat mirrors. One of the flat mirrors is positioned with 3 actuators for the tip, tilt, and focus corrections. The AOM will be cooled to about minus 55 degrees Celsius. The tertiary collimator assembly (TCA) consists of 5 optics and the supporting structure to relay the light beam to the coronagraph instrument. The TCA has 3 concave mirrors and 2 flat mirrors. One of the flat mirror is positioned with the 2 actuators for tip and tilt corrections. Most of this assembly will operate at room temperature with one mirror at about minus 7 degrees Celsius due to its proximity to the primary mirror assembly. The telescope control electronics (TCE) is the brain of the telescope. It is designed to provide thermal control using hundreds of heaters and sensors. The TCE will also control the secondary mirror's position with 6 alignment drives and 2 focus drives, and the AOM with 5 actuators. The deployable aperture cover (DAC) is responsible for keeping light out of the telescope barrel. This sunshade is deployed once in orbit using a soft material attached to support booms and remains in this position throughout the observatory's lifetime. The outer barrel assembly (OBA) will protect the telescope from stray light and help keep the mirrors cool. It also serves as the structural support for the solar array sunshield and deployable aperture cover. The OBA is connected directly to the upper deck of the spacecraft support system's primary structure with a series of struts that extend past the WFI and the coronagraphs. The communication module has 2 main instruments. The dual band HGA, which is the high gain antenna, fits in an S band 2 GHz, uplink downlink data for commands and housekeeping telemetry, and Ka band 26 GHz, high speed downlink data for science. In the use of pointing hardware called gimbals, the HGA can move in multiple directions to accurately point at ground station. A gimbal uses sensors and motors to stabilize and support any equipment, similar to what a tripod does for a camera on Earth. Telemetry is automatic measurement and wireless transmission of raw or semi-processed sensor data from the remote sources. The RF radio frequency communications electronics are located underneath the spacecraft bus on the communications panel. The Ka band transmitter is responsible for ingesting the high-speed science data from the science data recorder (SDR) and prepares the data for downlink to the ground station. The traveling wave tube amplifier provides very high output power for transmission to the ground through the high gain antenna. The science downlink can accommodate data rates up to 500 megabits per second. The solar array sunshield (SASS) is made of 6 solar array panels. The 2 center panels remain fixed while the 4 outer ones are deployed once in orbit. Hinge to fold down against the outer barrel assembly (OBA) During launch, the outer panels will ultimately swing up to align with the center panels. The SASs will be oriented toward the sun and provide power for the entire observatory. Its secondary function is to shade much of the observatory and keep the instruments cool. Observatory support system is the main body and structure that all other spacecraft pieces are attached to. It holds the electronics and equipment that support the space telescope and instruments. It has six components. The first one is the six-sided primary structure, also called the spacecraft bus, provides the structural support for the observatory. It contains six compartments or avionics bays the that house key electronics and components for running the rest of the spacecraft. It's made of a central cylinder with a top deck that supports the rest of the observatory and a bottom deck that interfaces to the rocket during launch. Next is the lower instrument sunshade LISs. Consists of two deployable panels attached to the spacecraft bus, which are designed to help shield the observatory from sunlight. The altitude control system ACS is a three-axis stabilized system that uses precision pointing to rotate the observatory to the right position for science. Six motorized flywheels called reaction wheels will enable the observatory to perform short, frequent movements to repoint at different regions of the sky required for science observation. The propulsion system will use hydrazine in its two types of thrusters used to maneuver the observatory. Hydrazine is a monopropellant, which means it doesn't need a second chemical to combust, only contact with the catalyst. Nancy Grace Roman Space Telescope will have enough fuel to operate for at least 10 years. Solar cells on the solar array panels will convert sunlight into power to provide approximately 4100 watts to the observatory's electronics while shading the spacecraft under it. The system includes a battery to regulate the voltage to all electrical components, provide backup power when there is no sun available to the solar array. This will not be used often because the observatory's orbit is at L2, will keep it in full view of the sun at all times. The command and data handling C&DH system is responsible for monitoring the health and safety of the observatory. This includes collecting telemetry and housekeeping data, monitoring temperatures, sending out hardware commands. It will also store up to 4 terabytes of science data in Science Data Recorder SDR for downlink to the ground when a ground station is in view. Roman's coronagraph instrument demonstrates technology that blocks the glare from a host starlight, allowing astronomers to directly image planets in an orbit around other stars. This module has six components: masks and optics. Coronagraph's masks block most of the glare from stars to reveal faint orbiting planets and dusty debris disks. The mirrors and lenses are finely polished to minimize additional glare or image distortions. Color filters will select which wavelengths of light to observe. Wollaston prisms will help measure the polarization of light from a star's disk, which tells scientists about property of its dust grains. A spectroscopy prism will spread a planet's light in two constituent colors, allowing scientists to study its atmospheric composition. Precision alignment mechanisms will finally position the coronagraph masks so they can effectively block starlight. The two deformable mirrors will help remove remaining starlight. They can bend and flex according to commands from the wavefront setting and the control system to correct for any small imperfections in the surface of other mirrors in the telescope or instruments. Each mirror is only about 2 inches, about 5 centimeters across, yet has more than 1600 independent actuators to adjust its surface. Every actuator is independently commanded with a precision better than 62 picometers, less than the diameter of a helium atom. This new technology is used in modern ground based telescopes but has never been part of a space based coronagraph. The Nancy Grace Roman's Space Telescope's wavefront sensing and control component will measure the irregularities in the light waves caused by diffraction and optical imperfections in the telescope and the instruments. It will analyze both the residual scattered Scattered starlight in the observation images and the light reflected by the coronagraph masks to sense errors like image motion, focus changes, and small imperfections in the shape of optics. The control system will then send compensating commands to the deformable mirrors and other instruments elements. The planets and disks that the coronagraph instrument will image are so faint their photons can arrive seconds apart. The EMCCD will detect these individual photons as they arrive. It has an operating temperature of about minus 130 degree Fahrenheit, approximately minus 90 degrees Celsius. The optical bench structures assembly provide a very stable base on which all of the optics, such as mirror, lenses, masks, and filters, are mounted. The bench is made from a composite material that is both light yet strong. It was mounted to the observatory through a set of bipods to a bolted surface. Thermal control systems will precisely regulate the temperatures of the bench, structures, mechanisms, and optics, which is crucial for optimal image quality. The electronics control the deformable mirrors, cameras, and other mechanisms. They are space qualified and radiation hardened to survive the rigors of spending years in orbit. The custom designed deformable mirrors electronics control more than 1,600 independent actuators on each deformable mirrors, more than 3,200 actuators total. The thermal control electronics send commands to heater that will keep key pieces of hardware temperature stabilized to within a few millikelvin. To help counteract spacecraft jitter, onboard processing will receive 1000 images per second from a camera and calculate tilt or tip commands to send to the wavefront control system. The Nancy Grace Roman Space Telescope will communicate through large radio antennas across the globe. Its ground systems will support mission and science operations, provide any necessary capabilities to process and archive the mission's data. These systems will be spread across multiple institutions. The following are a key to successful missions. First are the antennas, which will relay information between the observatory and ground stations on Earth. Ground stations will send command via the S band, which is 2 GHz radio signals, and speeds of up to 32 kilobits per second. Will also receive science data at the Ka band, which is 26 GHz, and speeds of up to 500 megabits a second, and engineering data at S band up to 680 kilobits per second. Using multiple contacts for several hours from each station, 1.4 terabytes of science data will be downlinked from the observatory each day, along with radio antenna at NASA's White Sands, JAXA, and ESA will continue the use of antennas they maintain around the globe. The Mission Operating Center (MOC) will command the spacecraft and perform observatory planning and scheduling. It will ingest, archive, and distribute spacecraft telemetry and monitor the health and safety of operation. The Science Operations Center (SOC) will plan and schedule science observation, archive missions science data, process images taken with the WFI, and perform initial GRISM and PRISM data processing. It is also responsible for calibrating the WFI and supporting the mission's launch and commissioning period. Finally, the SOC will provide science community engagement and public outreach support services to the project led outreach program. The Science Support Center (SSC) will run observations for the coronagraph instrument and perform the initial data processing steps. It will also process data for the WSI microlensing program as well as complete the processing of the GRISM or PRISM's assigned data. It will support the mission's commissioning period and lead the solicitation and review of science proposals. Finally, the SSC will provide science community engagement and public outreach support services to the project-led outreach program. The Coronagraph Technology Center (CTC) will work with the SSC and Community Participation Program to perform the coronagraph instrument with technology demonstrations. The Flight Dynamics Operation Area (FDOA) will determine the spacecraft's position and velocity to accuracies that allow for contact with the ground station and activities like planning maneuvers and determining the observatory's orbit. We'll also develop a support software for the ground systems so FDOA information can be delivered to the MOC, SOC, and SSC. I thank all my viewers for their support and enthusiasm. I thank my school teacher and my parents for teaching me, encouraging me, and helping me in accessing high quality content. Credits go to the respective sources for the extracts of information I understood. They are from the NASA website and their various departments, Wikipedia, various research papers, and books like Space Telescopes Capturing the Rays of the Electromagnetic Spectrum by Dr. Neil. This content is curated by me, but none of the sources has endorsed this recording. Thank you.